Hi. Now we will discuss the second part of transportation model, that is to test the optimality of a transportation problem. In the previous case, we have calculated the initial basic feasible solution by three methods. We understood how to calculate each method. Transportation problem, test for optimality. Once the initial solution is obtained, the next step is to check its optimality in terms of feasibility of the solution and total minimum transportation cost. An optimal solution is one where there is no other set of transportation routes that would reduce the total transportation cost, for which we have to evaluate each unoccupied cell in terms of opportunity cost. In this process, if there is no negative opportunity cost, then we will call the given solution as an optimal solution. If there is a negative opportunity cost, then the existing solution will not be an optimal solution. There will be a chance to improve the solution. So an unoccupied cell with the largest negative opportunity cost is selected to include in the new set of transportation routes. This value indicates that per unit cost reduction that can be achieved by making appropriate allocation in the unoccupied cell. The modified distribution method or MODI method is used to calculate opportunity cost associated with each unoccupied cell and then improving the current solution leading to an optimal solution. The MODI method is actually based on the concept of duality in transportation problem. MODI method is also known as UV method or method of multipliers. MODI method helps in comparing the relative advantage of alternative allocations for all the unoccupied cells simultaneously. Algorithm for MODI method. The steps to evaluate unoccupied cells are as follows. First step, for an initial basic feasible solution with m plus n minus 1 occupied cells, we will introduce new variables ui and vj for rows and columns respectively. And to start with getting the solution, any one of the ui or vj values we will put it as value as 0, then others can be calculated by using a relationship Cij equal to ui plus vj for all the occupied cells. And for unoccupied cells, we will calculate the opportunity cost with another relationship, that is dij equal to Cij minus ui plus vj. After that, examine the sign of the dij values. There will be three conditions. If all dij values are greater than 0, then current basic feasible solution is optimal solution. If dij is equal to 0, then the current basic feasible solution will remain unaffected but an alternative solution exists. If any one of the dij values, dij is less than 0, then an improved solution can be obtained by entering an unoccupied cell into the solution mix. An unoccupied cell having the largest negative value of dij is chosen for entering to the solution mix. After that, we will construct a loop for the unoccupied cell with the largest negative value of dij. Start the loop with the selected unoccupied cell and mark a plus sign in this cell. Trace a path along the rows or columns to an occupied cell. Mark the corner with minus sign and continue down the column or row to an occupied cell. Then mark the corner with plus sign and minus sign alternatively. Close the loop back to the selected unoccupied cell. From that, once we constructed the loop, then select the smallest quantity amongst the cells marked with a minus sign on the corners of the closed loop. Allocate this value to the selected unoccupied cell. Add it to occupied cells marked with a plus sign and subtract it from the occupied cells marked with a minus sign. Obtain a new improved solution by allocating units to the unoccupied cells according to step 5 and calculate the new total transportation cost. Thus, optimality of the revised solution. The procedure terminates when all the Dij values are greater than or equal to 0 for unoccupied cells. This is the algorithm. So in order to clearly understand the algorithm, we will take the same question which we have discussed for transportation model part 1. Obtain the optimal solution of the following transportation problem using MODI method. We are taking the same question here also. The initial basic feasible solution we have already calculated and we understood. The first algorithm is we have to calculate the initial basic feasible solution. So in this case, we will apply Vogel's approximation method and it is given as follows. As we know that Vogel's approximation method is very close to the optimal solution. Calculate the number of occupied cells 1, 2, 3, 4, 5 and 6, that is should be required. Number of rows plus number of columns minus 1. 3 plus 4 minus 1 is 6. So 6 occupied cells are there and the ring condition is also satisfied, 34. Sum of the supply, sum of the demands is equal to 34. So this is a initial basic feasible solution. And total transportation cost we calculated like this, that is 779 rupees. This is a non-degenerate initial basic feasible solution. So take this to calculate optimality. So as per the algorithm, the first step is introducing a new variable ui and vj into this IBFS. We will form the equation with the help of the following relationship Cij equal to ui plus vj for all the occupied cells. We have 6 occupied cells. We will give ui like this u1, u2, u3, v1, v2, v3 and v4. And we will make the relationship like this for the first occupied cell. This is u1 plus v1 which is equal to the cost element, that is u1 plus v1 equal to 19. Here u1 plus v4 equal to 10. Similarly for other occupied cells, u2 plus v3 equal to 40, u2 plus v4 equal to 60, u3 plus v2 equal to 8, u3 plus v4 equal to 20. As a variable v4 is used 3 times. You can see that v4 is used 3 times. You can easily identify from different color. So put the value of v4 equal to 0 and solve for the others. So once we put the v4 equal to 0, immediately we will get u1 equal to 10, u2 equal to 60, u3 equal to 20. By substituting these values into the other equations, you can easily solve v1 equal to 9, v2 equal to minus 12 and v3 equal to minus 20. This is for occupied cells. So once we obtained the value of ui and vj values, then we will calculate for unoccupied cells the dij. There is another relationship dij equal to cij minus ui plus vj. U and v values we have obtained and we have the cij values for each unoccupied cells. So it is easy for us to calculate the dij values. For example, this one. This is an unoccupied cell. This value is d12. So calculate the d12 like this. D12 equal to c12 minus u1 plus v2. Values are there. So 30 minus, here the u1 value is equal to 10, v2 value is equal to minus 12, 10 plus minus 12 equal to minus 2, 30 minus minus 2 equal to plus 32. This is the value that we have put here in a separate way. And for this cell d13 equal to c13 minus c1 plus v3, that is 50 minus, here the u1 value is 10 and the v3 value is equal to minus 20, 10 plus minus 20 equal to minus 10, 50 minus minus 10 equal to plus 60. So that is also we have marked here. Similarly d21, D22, D31, D33 you can easily calculate. Of all these values are we obtained plus 1 and plus 11 plus 70. Here in this case D22, C22 minus U2 plus V2, that's 30 minus 60 minus 60 plus minus 12, this is 48. 30 minus 48 equal to minus 18. Here we got a one negative value. So after calculating this, we have to check the sign of Dij value. If all the Dij's are positive or equal to 0, then the existing solution will be optimal. But in this case, we have a negative value. So immediately we have to go forward. We have to start a loop from that cell by this method. Start from that largest negative value. In this unoccupied cells, only one cell is having a negative value. So we will start from that cell. This loop we can make in the any direction, upward, left, right or downward direction, no issues. But the turning should be from an occupied cell. So this condition will not be satisfied in that case, because if we are going to left side, this is not an occupied cell, so we cannot turn from here. Similarly, we cannot turn go in this direction, because in the upward direction this is also an unoccupied cell, so we can't make a loop in this direction. At the same time, we can go either in this direction or in the downward direction, because in this direction we can have a occupied cells. From there we can turn the route. So going to the downward, and also from the starting point we have put a positive sign here, and we going down, this is an occupied cell, so we can easily turn in this direction, also in this direction. But the leftward direction is not possible because this is an unoccupied cell, so go in this direction till to the next occupied cell, and then turn from here, then go in this direction. You can go here, but you can turn here, but again it will not come back. So for that reason we are turning from this cell again back to this starting point. So we complete a loop like this, and in each turning point we have to put positive negative symbols alternatively. So we have started with positive sign here, so in the next turning it should be negative, and the next turning it should be positive, and next turning it should be negative, again come back, it should be this is a complete loop. So for the next stage, next iteration, next modification, I am taking the loop into the only this loop with the occupied element into the XM unit like this. So this is the loop. That loop I have reproduced here with 4 corners, one positive, negative, and each cells with the occupation. Here it's occupied with this. Initially there is no allocation here, so the value is 0. Here the allocation is 8. Here the allocation is 10. Here the allocation is 2. So all these things I have taken here. And in the loop, the new allocation is as follows. We will calculate the negative corners. We will look into the negative corners and identify the minimum allocation. That is, here the value is 2. That we will subtract from these two corners. 2 minus 2, 8 minus 2. These values are reproduced here, 0 and 6. The same 2 we will add in the positive corners. 0 plus 2, 2, 10 plus 2 is 12. So the table, transportation table is having a modified loop with a new allocation. It will be as follows. You can see this 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these 4 corners. 2, 0, 12 and 6 in these in the next table. So we have an allocation of 2 here and 6 here, 12 here. There was an allocation here that has gone in this case. The revised solution is given below. So now just count the number of occupied cells. Again it is 1, 2, 3, 4, 5 and 6 in different colors, you can easily identify. So that condition is satisfied. Number of allocations should be 6, m plus n minus 1. Number of rows plus number of columns minus 1, that is fulfilled. And now we have to again check for the optimality of this revised solution by introducing another u values and v values. So again introducing the u variable and v variable once again in this cell, and for the occupied cell we have a relationship Cij equal to ui plus vj. In order to calculate the opportunity cost for the unoccupied cells, we have another relationship dij equal to Cij minus ui plus vj. So we will take for the occupied cells ui u1 plus v1 equal to 19, u1 plus v4 equal to 10, u2 plus v2 equal to 30, u2 plus v3 equal to 40, u3 plus v2 equal to 8, u3 plus v4 equal to 20. This is the occupied cells. So by looking into the number of variables, almost all the variables are appearing 2 times. I have given u1 equal to 0 and solve for the test. Once we give u1 equal to 0, then we will get v1 equal to 19 and v4 equal to 10. With that we can easily calculate the remaining values like this. v4 equal to 10, by substituting that into this area you will get u3 equal to 10. The same you will apply here, u3 plus v2 equal to 8. So v2 you will get minus 2. The same v2 you will apply here, v2 plus u2 equal to 30 minus 2, and then you will get u2 equal to 32. So all the ui vj values we have obtained. With this we will calculate the opportunity cost for the unoccupied cells. So for that, take this cell, this is an unoccupied cell, d12 equal to c12 minus u1 plus v2, that is 30 minus u1 equal to 0 and v2 equal to minus 2, 0 plus minus 2, that is minus 2, 30 minus minus 2 equal to plus 32. Similarly, we can easily calculate d13 equal to c13 minus u1 plus v3, that is equal to 50 minus 8, that is plus 42 here. Here d21, that is a c21 minus u2 plus v1, 70 minus 19 plus 32. 19 plus 32 equal to 51, 70 minus 51 equal to plus 19. Here 60 minus 10 plus 32, 42. 60 minus 42 equal to plus 18. Here 40 minus 19 plus 10, that is 29 equal to plus 11. And here 70 minus 8 plus 10, that is 18, that is equal to plus 52. So all the opportunity cost values are, all the dij values are greater than 0. Therefore, the given solution is optimal. This is the way we will calculate the optimality by Modi method. After that, we will calculate the total transportation cost associated with this new solution. That is 5 into 19 plus 2 into 30 plus 2 into 10 plus 7 into 40 plus 6 into 8 plus 12 into 20. That we will calculate, and we got the value as 743 rupees. Again, the total transportation cost has been reduced. By the method of VAM, we got an initial basic feasible solution with the total transportation cost as 779 rupees. Here the total transportation cost has been reduced to 743. So this is the optimal solution. Hope you understood. Thank you.